So, um. All right, so before I start chapter 3, I want to ask you guys if you have any question about the remaining assignment. Questions for assignment number 2. Much of it has to do with naming or nomenclature, so I just want to make sure that you all understand what's happening here. If not, then we'll just move on to discussion on stoichiometry, which again is another topic that you would have encountered in introductory or high school chemistry. So let's get started with this. Of course, in order for us to deal with this topic, some things we need to recall. Molecular mass, that term, means the sum of the atomic masses of the atoms represented in the molecular formula. And that term is reserved specifically for molecules. Now, we discussed that ionic compounds do not exist as discrete units, such as molecules. So therefore, the corresponding term that we use as far as ionic compounds are concerned would be the formula mass, which in this case would be the sum of the atomic masses of the atoms or ions present in the formula unit, right? So it's very similar to molecular mass, but we do not use the term molecular mass when it comes to ionic compounds. We use the term formula mass, which is the sum of the atomic masses of the different ions present in a formula unit of the compound. So if you're asked, for example, to calculate the formula mass, where's my So if you're asked to determine the formula mass of ammonium sulfate, the first thing you need to do is determine the formula for ammonium sulfate, which is NH4, 2 oxide, and then SO4. So that's the formula. And then based on that, you determine the atomic masses of the different atoms present. Nitrogen is 14.01 AMU, plus 4 times that of oxygen, which is 1.008 AMU. And then all of that we would multiply by 2. And then to that, I would add the molar mass of sulfur, which is 32.07 AMU, plus 4 times the molar mass of oxygen, which is 16.00 AMU. And you add up all that, and whatever that gives, that would be the formula mass for ammonium sulfate. Okay, so that's basically that. Nothing too difficult there. Of course, you should also be familiar with the mole concept and the relationship between the mole, Avogadro's number, and the mass of a substance. So let's start off refreshing our memory about the definition of a mole. A mole is basically the amount of substance that contains as many elementary entities, and these entities could be atoms, molecules, etc., as there are atoms in exactly 12 grams of the carbon-12 isotope, right? And of course, because atoms are very small, then this would be a very big number, meaning the number of atoms, right? And that number that would exist per mole has been determined to be equal to 6.022 times 10 to the 23 mole to the minus 1. So basically, that represents the number of atoms, molecules, ions, whatever, in a mole of atoms, molecules, ions, etc. Right? So 1 mole is equal to this number of items. It doesn't matter really, literally, it could mean any item of any kind, but of course, in the context of chemistry, we usually are referring to small particles, atoms, ions, and so on, right? And just to give you an idea as to what we're talking about here in terms of the size of this number, it says 1 mole of oranges will weigh about as much as the Earth. So that gives you an idea as to how large a number this is, right? And please note that when you're abbreviating mole, you do not abbreviate it with uppercase M or lowercase m, right? Lowercase m represents meters, right? Uppercase M represents, as we're going to see later on, moles per liter. So normally we either write down this or we simply, and this is the best we can do in terms of abbreviation, we simply write down MOL, right? Not much of a difference from mole, but that's the best we can do in terms of abbreviating the mole unit. Okay, so this is just giving you some side-by-side comparisons between different substances and what happens when carbon and oxygen react to form carbon dioxide. So based on what we have here, it's a 1-to-1-to-1 molecule relationship between carbon, oxygen, and carbon dioxide, right? One atom of carbon will react with one molecule of oxygen to form one molecule of carbon dioxide. And we can extend that, we can double the numbers or triple or go as far as 1 dozen, right? Of carbon atoms, which will react with 1 dozen of oxygen molecules to give you 1 dozen CO2 molecules. And we can take that a step further to 1 mole, right? So basically, this represents the number of carbon atoms in 1 mole. That will require the same number of atoms or molecules of oxygen, which will require being produced the same number of CO2 molecules, right? And the difference between them, of course, would not be the mole or the number of molecules, but the masses, right? It turns out that 1 mole of carbon atoms have a mass of 12.011. 1 mole of oxygen will contain a mass of 31.9988 grams of oxygen, and 1 mole of carbon dioxide will contain 44.010 grams of carbon dioxide, right? And another thing that this also shows is the conservation of mass, because the sum of these two that combine together in this reaction will give the mass of the carbon dioxide being produced. So the important takeaway from this slide right here is that the balance equation, and we're going to talk about balancing equations later on, represents not only a microscopic relationship, atoms to molecules and so on, for the reaction that is taking place. You can also look at it in terms of the mole relationship, right? 1 mole of carbon will react with 1 mole of oxygen to form 1 mole of carbon dioxide, right? Okay, so that's that. So just to give an idea as to what 1 mole looks like for different substances, what you're looking at here is 1 mole of each of these substances: sulfur, copper, mercury, and helium, all right? And the question being asked here, how many atoms of helium are present? Avogadro's number, 6.02 times 10 to the 23. And the same answer will be true for sulfur, for copper, and for mercury, right? So the answer to all of these here would be Avogadro's number. Okay, so we talked about the mass earlier. So here's another definition that you should be familiar with. Molar mass, which is the mass of 1 mole of a substance. And it turns out that the molar mass numerically would be the same as the atomic mass, right? Or the molecular mass, or the formula mass, depending on the compound, right? However, the difference between molar mass and the atomic mass, for example, are the units. The molar mass of the units of molar mass is grams per mole, while the units of atomic mass or molecular mass or formula mass would be AMU. All right, so just to give you some examples here, 1 atom of sodium, and I should probably say 1 average atom of sodium, will have a mass of 22.99 AMU. But 1 mole of sodium will have a mass of 22.99 grams. All right, so the numbers are the same, but the units are different. This would be the units for atomic mass. This would be the units for molar mass. I think I have another example. In this case, the molecular mass of carbon dioxide is 44.01 AMU, but the molar mass of carbon dioxide is 44.01 grams per mole. And then in terms of ionic compounds, for 1 formula unit, the formula mass is 74.56 AMU, but the molar mass is 74.56 grams per mole. So numerically, the atomic mass and the molar masses, or molecular mass, molar mass, or formula mass, molar mass, are numerically the same, but the units will be different, right? Atomic mass will be expressed in atomic mass units, while molar mass will be expressed in grams per mole units, right? So this is just showing you the relationship between the mole, the Avogadro's number, and the molar mass, right? So sodium is used as the example here. 1 mole of sodium will have this many atoms, which will be, of course, Avogadro's number of atoms, and that number of atoms will have this mass, which is 22.99 grams, right? So that's the relationship between the mole value, Avogadro's number, and the molar mass. And therefore, based on these relationships, we can construct different conversion factors. Again, conversion factors that you're going to use is dependent on what you're trying to accomplish in terms of converting from one unit to the other. So we can express, for example, this relationship here. between the mole and the mass. And this here, which would be, of course, flipping this, you get this. Or you can use this relationship here. Again, it depends on what type of conversion that you are trying to accomplish, all right? Of course, depending on the question that you're given, you may need some preliminary or follow-up calculations in order to answer questions based on these sort of relationships. So just to give you a picture of the relationship between the formula of a compound and the mole relationships between the moles of the compound and the moles of the element. If you take this compound right here, right, 1 mole of that molecule will contain, based on the subscripts here, 3 moles of carbon atoms, 8 moles of hydrogens, and 3 moles of oxygen. So therefore, basically we can use the subscripts to tell the number of moles of each element present per mole of the substance, right? Here's another example, a bit more complex, but it's the same principle. 1 mole of ammonium sulfate will contain 2 moles of ammonium ion, and you can break this down to get 2 moles of nitrogen and 8 moles of hydrogen atoms. And then over here, we have 1 mole of sulfate ions, which can be further broken down to 1 mole of sulfur and 4 moles of oxygen, all right? So basically, the subscripts can be used to give you the mole relationship between the different elements present per mole of the particular substance, right? So let's look at this example based on what we have just learned. It says determine the mass of a 0.0750 moles sample of sodium. So I'm going to go through this quickly because this should be, sorry about that, this should be a bit of a review. Okay, so for A, the question gives you 0.0750 moles of sodium, and you're asked to determine the mass, presumably grams, of sodium, right? So what I would do is start off with what we're given, 0.0750 moles of Na, and then I will multiply by the appropriate conversion factor, which relates the moles of sodium to the mass of sodium. In other words, the molar mass. So the question now becomes, what goes up here as a numerator? What goes down here as a denominator? And the answer is that down here, you're going to have 1 mole of sodium, because you want this to cancel out with that. And up here, you're going to have the molar mass, which is 22.99 grams of sodium. And that's it, as far as the sum is concerned. Let's see what this gives. 0.0750 times 22.99. So according to my calculations, I got 1.72 grams of sodium, right? That's it, all right? So that's how you do that. Now, in the case of B, they gave you 62.5 grams of sodium, and they're asking for the equivalent amount or value in moles of sodium. So my question to you is, based on what we have done before, how will you do the B part? They gave you, write this down here, they gave you 62.5 grams of sodium. So my question to you is, what would be within the conversion factor here? What would go up top here, and what would go below here? Would go where? No? Oh, okay, so 22 is equal to 1.99 grams of sodium will go below, and 1 mole of sodium will go above. And that is indeed correct, because this will cancel with this in terms of the units. So the answer would be 62.5 divided by 22.99, and the answer I got is 2.72. 2.72 moles of sodium. Okay, very good. What about any questions about these? Any questions? Questions? All right, let me get rid of these here. Okay, so what about the C part? In the case of the C part, they gave you C, 1.00 times 10 to the 25 sodium atoms. All right? So the question is, what would be the mass in grams of sodium? So in this case, you're given a number of atoms and you're asked to determine the mass that that number of atoms would weigh, right? So what I would do is I would set it up such that we can go from the number of sodium atoms to the moles of sodium atoms. And then from that, I would go to calculating the grams of sodium. So what this suggests is that you're going to need two conversion factors in series. We'll start off with the 1.00 times 10 to the 25 sodium atoms, right? So my question to you is, how would we accomplish the first step going from here to here? In other words, what would be up here as a numerator and what would be down here as the denominator?
Use Avogadro's number
Okay, so where would Avogadro's number go?
on the bottom.
Right, so 6.02 times 10 to the 23 Na atoms. What would go above? 1 mole of Na, very good. So that this will cancel out with that. Okay, so the next step is now to convert from moles of sodium to grams of sodium. So again, what would go down here as the as the denominator, what would go above as the numerator? 1 mole of sodium below, 22.99 grams above. Very good. And that's it. This will cancel out with that. So whatever you get here in your final answer, the units will be grams of sodium. All right. So 1.00, oops, 1.00 times 10 to the 5, multiplied by 6.02 times 10 to the 3, and then multiplied by 2.9. So according to my calculation, I rounded out to 3 sig figs. The answer is going to be 381 grams of sodium. All right. And then the last one is interesting. The last one is asking for the mass of a single sodium atom. So basically, I can write this down as 1 atom equals to how many grams? 1 sodium atom equals to how many grams of sodium? So how would you do that? Start here. 1 atom of sodium. What would you multiply that by?
Do Avogadro's number on the bottom and 22.99
Okay,
on the
let's
top.
try that. Oops. 6.02 times 10 to the 23 sodium atoms. And what goes above?
22.99.
22.99 grams of sodium above. That's exactly it. So let's see, because this will cancel with this. So you'll be left with grams of sodium, which would be equal to the mass in 1 atom. So that's 22.99 divided by 6.02 times 10 to the 33. So according to my calculation, the answer becomes 3.82. 3.82 times 10 to the minus 23 grams, right? That's it. Okay? Any questions? Okay, moving along. Again, another topic that you should have met before. Certainly would have met it if you had me for intro. And that has to do with percent composition, specifically mass percent composition. Stick a bit. You know what? Before you even get to that, Let me start you off on assignment 3.
Thank you.
And I want you to focus on question number. Well, definitely number 1. Let me see here. Number 1. Okay, number 1, that's it. All right. And let me check for you guys out there in Zoom. Let me check to make sure that it's published. Okay, it's published. So you guys out there in Zoom, you can download it and get started on it. You should be able to make quick work of it, but if there are any questions, that's what I'm here for. In the meantime, let me take roll, which I forgot to take at the beginning of class. All right, so Amo here. Bessie is here. Bishop. Bragg. Cornell. Chester. Cowood. Erlinson.
Here.
Gerard. Green. Kennedy. Leonard. Mohammed Boy is here. Spall.
Here.
Sullivan.
Yep.
And Swistak is here. On A? Or B? Okay, so let me. Okay, so D is asking for the number of carbon atoms in 10.5 grams of C6H12O6. So what I would do first is start off with, of course, the 10.5 grams of carbon of C6H12O6. All right, and then I'll convert that to moles, right? So we're gonna have 1 mole of C6H12O6. And I'm gonna need to find molar mass of all of that. So since I'm lazy.
$120.01.
Sure. C6H12O6. But according to this is 180.16. So I would put.
How's that also much?
Well. This breaks it down for 6 carbons, that's 72.06 total. For 12 hydrogen, that's 12.09. And for 6 oxygen.
I see where I messed up.
Oh, okay. Okay, so what am I doing here? Okay, so down here I'm going to put 180.16 grams of C6H12O6. And then this will cancel with that. Then what I would do here at this juncture is find out the mole relationship between the moles of carbon and the moles of the compound. For the formula here, you have a 6 right here as a subscript, right? So that tells me that there are 6 moles of carbon for every 1 mole of C6H12O6. So this would go with that. And then finally, to get the mass of carbon, not mass, I'm sorry, the number of carbon atoms. Avogadro's number is what you're going to use. So 1 mole of carbon will go down here, and 6.02 times 10 to the 23 carbon atoms will go up top. So this will go with that. And then we do the number crunching. So that's 10.5. 10.5 divided by 180.16 times 6 times 6.02 times 10 to the 23. And according to my calculations, the number of carbon atoms would be 2.11 times 10 to the 23 C atoms. That's it. All right. Okay, so can I create this? All right, so we're gonna move on now to a discussion of percent composition, as I said before. This is something that you should have met in your introductory or high school chemistry. So when we talk about composition, usually with respect to compounds, usually we're referring to mass composition or composition by mass percent, all right? And here's the definition right here. Basically, it is expressed as the mass of that particular element over 100 grams of the compound, or another way of stating it is the mass of the element divided by the mass of the compound times 100%. Right, so you can use either one of these two. you're both just as correct depending on the information that you're given, right? And it's very easy, as you can see, to calculate the mass percent. So for example, based on that formula, so for example, if you're given a compound like butane, which has a formula C4H10, then we can say that the percent, of carbon will be equal to 4, because of the subscript here, multiplied by the molar mass of carbon, which is 12.01 AMU, right? Divided by the total molar mass of everything. So you'd have to calculate that. Probably should have done that before. 4 times 12.01 AMU plus 10 times 1.008 AMU. So this will give 48.04 AMU plus 10.08, 10.08, I'm sorry, AMU. So when you add these two together, you're gonna get 58.12 AMU, all right? So that goes down here, 58.12 AMU. And then we do a similar calculation for the hydrogen. This will be 10 times 1.008 AMU divided by 58.12 AMU. So 4 times 12.01 divided by 58.12 times 100. So for the carbon, that would be 82.66. 82.66%. And then in the case of hydrogen, 10 times 10 times 1.008 divided by 58.2 times 100. And the answer I got here is 17.34%. And of course, since these are the other two elements present, if you add both of those percentages, you should get, if not exactly 100%, a number very close to 100. So if you add 82.66 plus 17.34, I got exactly 100%, 100.00%, right? So that's basically how you deal with determining the percent composition of a compound, right? Very simple concept. Now, well, before I leave this straight, any questions about this? Any questions? Any questions? All right, so I'm going to leave these two for you guys to try on your own. These are just two examples. The first one is asking for calculating the mass percent of each element in ammonium nitrate. In order for you to answer that question, you'd have to know what the formula for ammonium nitrate is. And then the next one, it says how many grams of nitrogen are present in 46.34 grams of ammonium nitrate. So the answer that you get from the first example is what you're going to use to answer the question in the second example. So I'm going to leave that for you guys to try on your own, all right? What is more challenging is determining the formulas for a compound if you're given the percent composition data, right? That's not as easy as what we have just seen just now. So basically, there are a couple of steps that are involved. And again, this is something you should have met before in your introductory course. The very first thing you're going to do is determine either the percentage or the mass of each element, right? So it depends on the information that's given to you in a question, right? Some questions will give you the percentage of each element. Other questions will give you the actual mass of each element that is present, all right? Now, if you're given the percentage, and you're going to see how this works in the example I'm about to do, if you're going to be given the percentages, then you'd have to make an assumption. And the assumption is that the mass of the compound is of a certain value. Now, that value could literally be any number, but we like to use 100, right? Because if we assume that we're working with 100 grams of the substance, then those percentage values will represent the mass in grams of each element present in the compound, right? And you're going to see that being done in the examples that I'm going to look at. The other step that you need to take is that you're going to determine the whole number ratio. Well, first, before that, I'm jumping a step. What you need to do next is find the moles of each element based on the masses that you have obtained. And then after you find the moles, then you find the simplest whole number mole ratio for each of the elements. And that will give you basically the empirical formula, all right? And the way you determine that whole number ratio is that you identify the smallest mole value and divide everything by that mole value. And hopefully you're going to get some numbers that are, if not integers, very close to integers. Now, there may be some instances where you don't get clear integers, and there's an additional step, which I'm going to get into as well, right? So we're going to look at each of these examples here. So let me, I'm going to need some space. Come on. I'm going to need some space. What I'm going to do is copy this. And let me see if I can paste it onto this here. Okay. So, okay, I'll just go to using the last question. So the question says, it's talking about phenol, it gives you the percentage composition of each element by mass. And the question is asking for you to determine the empirical formula. So the way I like to do this, I like to do this in a tabular form. So let me do it that way. You have carbon, hydrogen, and oxygen. Those are the three elements present. And as I said earlier, what I would do, since we're given the percentage by mass data for each of the elements, I would assume 100 grams, right? And I would assume that I'm working with 100 grams of substance, which means that the mass of each element will be reflected in these numbers, which are the percentage values. So therefore, this would be 76.57%, or grams, I should say. This would be 6.43 grams. And the last one will be 17.00 grams, right? So that's the first step. The next step is to determine the moles. And we all should know how to do that. Basically, what we do is divide each of them by their respective atomic masses. So in the case of carbon, that would be 76.57 grams multiplied by 1 mole over 12.01 grams. In the case of hydrogen, that would be 6.43 grams multiplied by 1 mole over 1.008 grams. And then in the case of oxygen, that would be 17.00 grams multiplied by 1 mole over 16.00 grams. All right, and then we do the calculation. And please, I always say, do the calculation yourselves so that I'm not leading you guys astray. Okay, now for carbon, when I did that calculation for the mole value, I got 6.376 moles, right? In the case of hydrogen, 6.43 divided by 1.008, and I got 6.379 moles. And then in the case of oxygen, 17 divided by 16, I got 1.063 moles. And then now we divide it right through. Well, firstly, we identify which of these mole values is the smallest obviously that would be this one. So I'll divide each of these values by 1.063 moles, right? So 6.376 moles will be divided by 1.063 moles. The same thing will be true for here, 6.379 moles. I'll divide by 1.063 moles. And then the last one, when divided by itself, will give you 1, right? So let's do the calculation for this part. 6.376 divided by 1.063. And according to my calculations, this rounded up to 4 sig figs will give 5.998. And then in the case of hydrogen, 6.379 divided by 1.063. According to my calculator here, the answer is 6.001, right? Now we can see clearly that 5.998 is very close to 6, and 6.001 is very close to 6. So therefore, the empirical formula will be C6H6 O. That's it. Right? Okay, any questions about this one? Any questions about this example? Any questions out there in Zoom?
Can you scroll back down for a second, please?
Yeah. Okay, are we finished with this? All right. The next example, let me go back to the PowerPoint here. Different compounds, again, they gave you the percentage composition. So let's see if you can do this one here. Let me copy. All right, let me paste it here. Okay, so same 3 elements, numbers are different. So let me set up my table again, carbon, hydrogen, oxygen. We do this, and that, and that. Right? So the numbers are 45 for the masses, because again, we're assuming 100 grams, right? So the numbers are 45.27 grams of carbon, 9.50 grams of hydrogen, and 45.23 grams of oxygen, right? So what's the next step? Based on the previous example. Okay, so moles, so in the case of carbon, 48.27 grams multiplied by 1 mole over 12.01 grams. What about hydrogen? 9.50 grams multiplied by what? 1 mole over. What's the molar mass of hydrogen? 1.008 grams. And then in the case of oxygen, it's 45.23 grams multiplied by 1 mole over.
30.
No, not 32. 16.00 grams. Okay. So we need to work these out. 48.27 divided by 12.01. So the answer I got for this one, rounded off to 4 sig figs, would be 4. Yes, sir.
Isn't it 3.5?
Right, thank you very much. We made that correction right now, so this should be 45, this should be 45. 45.27, 45.27, so let me redo this. 45.27 divided by 12.41. Okay, so the, here is this. So according to my calculations, this works out to equal to 3.769 volts. And then we divide 9.5 divided by 1.008. And I got 9.42 volts. And then in the last one, 45.23 divided by 16, and I got 2.827, all right? Okay, so now that we have the mole values, what's the next step? We're divided right through by the smallest of these values, and we can identify the smallest value as being this, right? So we're gonna divide right through by 2.827 moles. We're gonna get 3.769 moles divided by 2.827 moles. 9.42 moles divided by 2.827 moles. And this will give you 1 divided by itself. So let's work out for the carbon, 3.769 divided by 2.827. And according to my calculation, when we run it out to 3 sig figs, this becomes 1.333, right? And then in the case of hydrogen, we're going to divide 9.42 by 2.827. And this gives you, when rounded up to 3 sig figs, 3.33, all right? Now, in this case, things are a bit different compared to the previous example, because now we're ending up at this stage, we're ending up with numbers that are not anywhere near integers, all right? Not near to the closest integer, right? So when you get to a situation like this, what you'd have to do now is identify an integer that when you multiply that integer by those numbers will be converted into integers themselves, right? Now, you can get a hint as to what you should multiply by, depending on the type of digits that follow the decimal point in these numbers. In this case, we have a recurring 3 after the decimal point. And as you all should know, 1/3 is equal to 0.333 recurring, right? So if you want to convert this number, which is this number, by, well, into an integer, you have to multiply by 3, right? Right, 3 will cancel out there and there, so therefore in that case, the answer is going to be 1. Now in this case here, if you multiply 1.33 by 3, which you have to do straight across, that 1.33 will become 4, right? Do it on the calculator, 1.33, 3 times 3 gives you 3.999, which is approximately 4, right? And then 3.33, when multiplied by 3, will give you 9.99, which would be 10. And of course, 3 times 1 will give you 3. So in this case, the empirical formula would be C4H10O3. And that's how that is done. All right. So you might end up encountering a situation like this, and we can get a hint as to what you should multiply by. If you have a recurring 3, in fact, let me make a list here. Oops. If you have a recurring 3 after the decimal point, so if you have something 0.333, then what you do is multiply by 3. If you have something 0.666, recurring 6 after the decimal point, then you multiply by 3. If you have something 0.5, you multiply by 2. If you have something 0.25, you multiply by 4. If you have something 0.75, multiply by 4. If you have a recurring 1 after the decimal point, multiply by 9. What else? Those are the more obvious ones. Now, there are others which are not as obvious. And what that means therefore is that you have to just basically use trial and error. You have to just multiply by certain integers and see if you can get that number converted into an integer. All right? Okay, so any questions about this example? Any questions? Okay, so now you should be able to do. I want you guys to try now. Question number 2 before we move on to question number 3. Question number 2 is just basically an exercise in calculating percentages based on your formula. So it's similar to an example that we looked at earlier. I'm going to call it a day. In the meantime, in addition to question number 2, you should also attempt question number 3, all right? And if you have any problems, please feel free to contact me. Either in person or via Skype during my office hours. Oh,
If you only do the day with card, think about paying card. Yeah, but there's no option for paying with card. It's 10 cents more. It's 10 cents more. It's 10 cents. So 10 cents. And it's like $2.